talk about quantum transport, especially in the context of electric baryogenesis. And I guess I don't have the time to give a full-fledged lecture on thermodynamics and QFT and all that. But I just try to motivate where those quantum equations which we use in electric baryogenesis come from different sides, from classical physics and from WKB approach and all kinds of different things, and finally, eventually, you might believe that the equations we use are correct. Okay, so yeah, the outline is the following. First, I'll give a short motivation. I mean, we heard talks about electric baryogenesis already yesterday, so we'll be rather fast in this part. And then I give a couple of classical pictures how transport might work. So, for example, the reflection picture, or also the Boltzmann equations. And then I will motivate how, and then show you the kind of fine equations, which is the basis of our work in electric baryogenesis. And try to get all those pictures together and show how kind of fine equations can really reproduce transport in all kind of different regimes. And depending on the time, eventually I will show you how in those different regimes those different limits play a role in different models like MSSM and NMSSM. Because in those two models, the p-violation and transport in some sense works in completely different ways. Okay. So first slide of every baryogenesis talk is basically the Sakharov conditions. So the famous Sakharov conditions basically state the ingredients you need for doing baryogenesis. So you need to violate baryon number, charge and charge parity conjugation, and also you need some certain source of non-equilibrium physics in order to explain the baryon density of the universe, which is this small number. So how does it work in electric baryogenesis? First of all, the simplest ingredient is basically the solvent, which violates B. It also violates L, such that B minus L is conserved. But basically that is effectively the operator which provides the baryon symmetry as a baryon number violation. And besides, of course, violates C, because it just couples to the left-handed. Second ingredient is out of equilibrium physics, and that's the main topic of this workshop, which is electric phase transition. So, during the electric phase transition, we have a Higgs wave, which changes along this bubble wall, and this will drive your plasma out of equilibrium. And this is a rather violent process because those bubbles expand with the velocity of light, more or less. So that's basically the picture we talked about in the last couple of days. And finally, CP violation, and well, the most prominent example is the NSSN. The CP violation usually comes from the mass of the particles in the plasma. So if you have different Higgs waves which change along the bubble or profile, you can induce some CP violation in the wall. So some more pictures how that works in principle. So what you have is those bubbles of Higgs wave which rushes by, so it has a certain velocity and has a certain thickness. And now this mass, which is changing along the Higgs profile, should in some way induce some CP violating effects in the wall such that you get CP violating particle densities. For example, the quarks, leptons, or vaginos. Then the next step is that you have this follow-on which violates a baryon number, which is active outside of the bubble but is suppressed in the bubble. But however, that doesn't work so well as long as your CP violating particle densities are just close to the wall. So what you need in addition is transport or diffusion. So somehow you need to get this effect close to the wall into the symmetric phase such that the solenoid really actively can act on this CP violating particle density and produce a baryon number. So what you need to have in your system, or your formulas, what they should describe is CP violation and transport. So and somehow that's kind of a long stretch because CP violation is a quantum phenomenon, while transport usually is described by the classical equations like Boltzmann equations. Okay, so I think that's the basic picture which we established in the last couple of days, but I think there are some people which haven't been there in the last couple of days. So I mean, if there are questions about this basic picture, how electric baryogenesis works, it might be actually the right time to ask. Okay. So now I would like to talk about different ways of establishing or describing transport. And the most intuitive picture, I think, is particle reflection in a wall. So what you have here is basically, again, this picture of this Higgs wall. So the Higgs wave changes, and because the Higgs wave changes, the mass of your particles in the plasma change, right? So somehow the particles get a delta M if they would like to pass this bubble wall. Right? And you know that as long as the wall doesn't move, so this is the case V equal to 0, you know that somehow equilibrium should be a steady state. So if you now look at the microphysics, what basically happens across the wall is that particles just replace other particles. So what you have for the soft modes cannot climb this potential, right? Because you know that your background just depends on Z, so the energy of the particle will not change. But the Pz of the particle will change such that you again have the same dispersion relation just with a different mass in this phase, like in this phase. So the soft modes necessarily, at least in classical approximation, will be reflected. So they come here, they're reflected, and of course, close to the wall, there will be equal numbers of those guys as those guys, because they just get reflected here. And far away from the wall, you also know that they are an equal number, just because your wall is static, so your plasma is at rest in respect to your wall, so you know that those guys have to be in equal numbers. Likewise, the modes which have large momenta, they can of course pass this wall, but the Pz gets changed. But nevertheless, you know that since the distribution functions just depends on energy, there will be equal numbers of those guys and those guys. So after all, what happens in the case of a static wall is just that all the particles replace the other particles. Some go this way and replace those guys, some go this way, and everything just replaces everything, and you are in this steady state. So in this relation, you're in equilibrium, and it's completely consistent with the picture of particles just flying around without any interactions. But the picture, of course, changes when you switch on some small wall velocity. So you still can. So what I want to discuss now is again the whole picture in the wall frame. So it's a co-moving frame in the wall, but this time, if you are in the co-moving frame, the plasma does not depend on the energy, but it depends on the following combination, right? So that's one thing you have to keep in mind. So what will happen to the soft modes? The soft modes just will be reflected, like in the old case. So you know that close to the wall, those modes and those modes have equal numbers. But you know that far away from the wall, since the plasma is moving against the wall, you know that there are more modes which are moving against the wall, or to put it the other way around, those modes have equal numbers. So if you compare modes which have equal numbers, you see that there's a net momentum against the wall. And because of that, you would expect that somehow to come from this situation to this situation, you need some equilibration and some shock front. I mean, you also can have some build-up. So if the wall is moving, a lot of particles are reflected, some momentum is transferred on the wall, and you have some build-up of flow in front of the wall, like a shock front in hydrodynamics. At the same time, if you do it for the hard modes, you also see that it doesn't fit anymore. So there are more of those modes than those modes. So somehow you need some equilibration behind the wall as well. You're out of equilibrium behind the wall, and somehow the system will equilibrate, and you will get some flow behind the wall, just because of this momentum transfer. There's one more interesting limit, which was discussed recently by Bödecker-Moore. And just discuss it because in this limit you can make easily contact to the equations we will use later on, the Kalanov-Prime equations, and that is the limit of really, really high wall velocities. Because in this case, there are basically no soft modes. So the plasma is really strongly hitting against the wall, and soft modes are exponentially suppressed. And so the only effect you have to take into account is you start with the plasma on the right-hand side. You just cross this barrier, you know how the Pz momentum changes, and then you know what is your particle distribution function. And basically information cannot go into the right-hand side because you would expect that diffusion and all transport effects cannot propagate faster than the speed of sound. So what you can do is you start with the equilibrium state here, just cross this barrier, take this effect into account that the PZ changes, and that's it. Then you know what your state, especially close to this kink, will look like. And you can use that, like Burdick and Moore did, to calculate the friction of the wall, which is produced by this kind of effect. So that's kind of a really intuitive picture. You have particles hitting a wall and are reflected or not. And but there's something wrong why you cannot use this in baryogenesis, and that's because this is only valid for thin walls. So if you have a wall which is rather a continuous profile, you will have multiple reflections and all kind of different effects which will make this kind of picture a little bit uglier and will make it harder to really calculate things. And in addition, of course, there's no CP relation in this picture so far, so you have to include CP relation. So that's the reason why one would like to have a different picture of calculating this effect of the wall.
Why did you say this is only valid for thin walls?
Okay, I mean
it's valid for walls which appear to, for which there is no reflection as part, for which there is no scattering as part of the crustal wall.
I mean, let's say you have a thick wall, right? I mean, then you can have multiple reflections. I mean, that was partially studied, and you get some logarithmic effects, but it makes it harder in some sense.
And the second, the scattering rate goes as mean free path goes.
Yeah, and then there's the second effect is of course mean free path. So
yeah, but mean free path I think will be longer, right?
Well, depending on the point.
Yeah, but I mean, if you have a right, I mean, it depends how the different scales work. But so even if you don't have interactions, you might have complicated effects on the wall. So it's I mean, you need a differential description of this effect. You cannot say, okay, I'm passing the wall and that's it. And besides, I mean, if you include CP violation, it's not just you get reflected or not. I mean, you have to calculate reflection coefficients, quantum physics.
Yeah.
Right. And then if you have a continuous wall, everything gets a little bit messier. But after all, I mean, you would expect that you end up with kind of binding equations anyway. So I think in some sense it's easier to go directly to kind of binding. Okay, so but before I explain kind of binding equations, I would like to give some requisites to that. First of all, as I said, there are certain conditions you have to fulfill or ingredients you need for baryogenesis. And the first one is, as I said, thick walls. The second one is CP violation, which was not included in this reflection picture yet. And the third one is transport. I mean, we had not really transport in this reflection picture, which would be of diffusion or Boltzmann type. It was just a really, really simple picture of what happens close to the wall and why you might get some flow or some effect on the plasma from the changing Higgs wave. Okay, so first I would like to remind you how to derive classical Boltzmann equations and to show you how they look like. And it's basically what you have is you have a classical particle distribution function. So you have a phase space. So you just count the number n of particles which are at a certain position at a certain time with a certain velocity. Right? And then you ask the question, okay, what happens if I now wait for a small time delta t? What will happen to this function n? And you know that the position will change by the velocity times theta t. And you know that the velocity will change by some force times theta t in case there's some force present. And you know that the difference between this guy and this guy will be due to interactions. So some collisions in the plasma, scattering, whatever. And if you now take the infinitesimal limit of this one, you get the Boltzmann equation. So you have a time derivative. This is basically just a free streaming. That your particles just are flying without any interactions. This one is changing momentum due to the force, and on the right hand side we have some collisions or interactions. So the big question is now, how can you include the P relation in such a picture? And the first problem is that of course in quantum physics you don't have a phase space. So I mean, just if you think about it, how could you construct or how could you read off something classical like a phase space from something which is quantum by construction? And of course you have to do that because you would like to include the CP relating effect, so somehow quantum physics has to answer. And it turns out that by now there are different approaches to do that. And I will not explain all of them, but basically just explain later on the Kadanoff-Beim approach, which I was working on for my PhD thesis, and then I will comment which of these results reproduce former results. So the first one was a WKB approach. So what you do is instead of just saying, okay, I have particles which reflect, you look for, you solve for a quantum, well, let's say Dirac kind of equation, and in the WKB approach, and try to read off a force. So what you do is you look at a WKB effect and then try to figure out what is this F. So that's basically this first approach, which was pioneered by Joyce Kainoline and also Joyce Prokopec and Turok, and which still can be used in certain models. But I will comment on that later on. But however, it turned out that if you count h bars, for example, this effect is h bar squared. And secondly, it doesn't contain any flavor mixing. And
why do you say it's h bars?
H bar, not h bar squared.
Well, it depends how you count. I mean, there's a it depends how you count. I mean, there's an overall h bar squared in the kinetic, but also the kinetic term comes with the h bar. So of course, it's leading order. And I mean, you would say.
Classical force is all the h bar 0, and this is h bar.
Yeah, you would say this guy basically is it's a quantum effect, so in leading order.
Yes.
Right. But also mixing is a. But I mean, if you naively count h bars for the mixing effect, it's h bar to the 0. But still, it's a quantum effect because it's still in
1 over h bar. 1 over h bar.
Oh, well, I wouldn't say that. Because, I mean, in the limit of large oscillations, this effect vanishes because everything oscillates and the integrated effect is 0. Right. So even though the source is h bar to the 0, the integrated effect is
sure.
h bar to the 1. Right. Because you get a...
But you wouldn't say that classical Boltzmann's equation is order h bar, right? That's order h bar to power 0.
No, but that's just how it comes out if you count h bars in Kadanoff-Beim. I mean, it's easier concept than asking, okay, what's classical physics if you take the right limit. Right. But it turns out if you just look at sources, then naively, then this guy has 1 h bar more than this one. So you might argue that in certain windows, mixing effects or flavor effects are important, especially in a model where you don't have any source of this kind, like in the MSSM. So it depends on the model which of those two effects is dominant. And of course you would like to have but somehow it's different physics. So somehow you would like to have a unifying approach to which reproduces both results, and that's basically what the Kadanoff-Beim approach does for you. Just to show you that it's really different physics, I wrote down here some different characteristics and how people do it. And in the WKB approach, what you do is you have the mass eigenbasis, you follow basically pseudo particles, and what you basically do is you calculate this force and put it into a Boltzmann type equation. But you don't have any mixing, so that's the big point. And then there's also a little bit a problem here because some people, for example, claim that this effect is just an artifact because you have a kinetic momentum and you have a physical momentum. So you don't know if it's hard to decide just by WKB if this is really physics.
That was the beauty of the whole approach, the relation. That's what is the proper momentum.
Yeah, but I think still some people claim that you can gauge it away, so to speak, by absorbing the effect into the wave function, right?
Eventually, not this the, I would say. This is gauge independent. It's manifestly gauge independent. Definition.
Yeah, I just can tell you what I saw in the literature, and I saw the claim that you can gauge it away.
I wrote part of that literature.
I don't want to defend the statement.
No, I mean, this was sort of long and hard. Actually, I was the one to suggest momentum, and the basis was that this is the guy which is independent of the gauge.
Yeah. But that's why I put it.
But nevertheless, you're right. It was very nice to see it emerging from the Kadanoff.
Yeah, so in some sense the Kadanoff-Beim equation reproduce the result by those. Sure. Okay, and then on the other hand, if you
Konstandin first discovered it from Kadanoff Bay from a slightly different point of view than you are going to see now.
Yeah, I mean, it was actually it was the first thing that I derived it through the propagate equation, and that agrees with Kimo's derivation.
Yeah.
And so we published it as separate papers, but in fact, it was only published when we had agreements.
Okay.
So that's the true history. And,
okay, on the other hand, those a little bit newer mixing approaches really perturbative. So what you do is you calculate some quantum deviation from equilibrium, and then you just put by hand this information in some kind of diffusion equation. So in the second approach, the biggest weakness is basically that you really have to fill this gap between classical diffusion and CP relation, which is a quantum effect by hand. So, I mean, this step is really not under control in this approach, which was first invented by these people. And secondly, there are a couple of other problems like the finiteness in this perturbative approach, which is not always guaranteed, and also the question of basis, because you want to look for a flavor effect, but nevertheless you do the calculation in a specific basis and neglect off diagonals. Okay, so now comes more or less the main part of the talk, which has to do with the Kadanoff prime equations. And but as I said, it's nothing you can really derive from a couple of pages. So I just want to show you, or just show you the form, and it might remind you of equations you've seen before, so that after all you might think that's a reasonable thing to do. So what the Kadanoff prime equation basically is, it's just a statistical analog from the Schwinger-Dyson equations. So this is your inverted propagator, that's your self-energy, and that's your two-point function, right? It might be a boson or a fermion, it doesn't matter at this stage. Okay, but what you don't want to calculate are, what you usually do in QFT is you calculate S matrix element. So you have some particle, you prepare this particle state, then you have interactions, and finally you project on what's coming out, right? So, but what you want to do here is you want to somehow do QFT, but with a density matrix. You want to have a statistical state. So what you do is you start with a so what you want to do is you want to, for example, calculate something which is time dependent, and you start with some density matrix, and what you of course do, you take the trace of this guy, so something like this, right?
it's almost impossible to read.
Can we? This is reliable, but
Better.
much better. Okay, so you want to calculate something like an expectation value of some operator, and how you do that is just by using the density matrix and taking the trace. But what you have to do in practice, you have to, let's say you want to do it at a certain time t, what you have to do, you have to evolve your density matrix from your initial time t0 to t. And how you do that, if you have a state, let's say, you call your state A, B, which is element in your density matrix, you have to do it with the IH delta t here, and you have to do it with the minus IH delta t here. And when you do it in QFT, what you get is you get not just an integration from some initial time to some late time and some interaction between, but what you get is you first have to integrate to infinity or to some late time, and then you have to integrate back. So this basically is your cat state, and this is basically your bra state. So what you have to do is, instead of just integrating from minus infinity to plus infinity, you have you have two passes in your times, which are in x, y, and z here. And another way of writing it is just by splitting this part into two parts and then generating a 2x2 matrix structure. Right? So T basically means that two times are on the upper part. Larger means the first time is on C plus and the other one is on C minus. This one would be the other one, it's vice versa, and this is basically time enter ordered, which means both times on the C minus branch. So what you get basically is you get this additional 2x2 matrix structure in the current prime equation. So that's the first difference. What did I do now? Okay. Back online. Okay, so you get this ugly 2x2 structure, which makes calculations, of course, more complicated.
So can you comment also on the first equation again? So
basically, the form is exactly the same like you would expect in a Schwinger-Dyson equation. It's just coordinate space.
yes.
No, you just have a 2x2 matrix structure.
Yeah, I mean, it's just a convolution. I mean, if you go to Fourier space, it will be multiplication. Right. So if you write down the Schwinger-Dyson equation, coordinate space is exactly this one.
And it's just an identity for the prop operator.
For the two-point function, yeah.
That's also a definition of sigma, basically.
Pardon me?
What's
So
the
the-
definition of sigma, I forgot.
Yeah,
That's the definition
kind
of
of.
sigma.
Yeah. Yeah. So usually you would divide by this guy, and then you would see that it's basically.
But of course, you can actually derive it from the effective action. But 2pi effective
2pi.
action.
Well, it's just you can also see it as a diagrammatic identity, I suppose.
Exactly. So
But you can write it diagrammatically, but also you can write it
so
effectively
this is sigma.
at the exactly. And then if you write it at the level of effective action, this is just
You can see this way.
right. The sigma is just the derivative, functional derivative of the effective action with respect to the property.
Yes. So
Let's just multiply it with the inverse of S0, so that doesn't look like it. Nothing else.
Yeah.
mm,
But the form is the same like in usual QFT. No big surprise here. It gets a little bit more complicated because all your two-point functions in the context of now don't just depend on the relative coordinate like in usual QFT, but you also get direct dependence on the average coordinate. So if you now do the Fourier transform, instead of usual multiplication, you get a Moyer star product, which is usually written in this with this diamond. So you get a kind of complicated differential operator which connects those quantities now. So in usual QFT, there's no direct dependence. So basically, you would have this guy goes to 1, right? And then you just get this equation, but just usual multiplication. That's
It's basically Poisson bracket. Right?
there should be something else here. Okay.
No, but this is also basically Poisson bracket, right?
No, I mean first order is a Poisson bracket.
But you wrote the definition is the first order.
Yeah, exactly. I mean the Moyer star product is the exponentiated Poisson bracket in some sense.
Oh. Okay.
Right. So the first order will be a Poisson bracket, and the zeroth order will be just usual multiplication. Okay.
and these sigmas and so on, they are now a function of this whole time contour. They are
Not anymore because I have this 2x2 structure. So I mean you can
just
either
a
do
function
it,
of normal time.
right, but you have to remember that for example in those elements everything is intertime ordered.
And that comes from this simple picture. This B evolves in an intertime ordered way.
So what you do here is you have to path order. So if you have a
Bra.
time here and you have a time
Not the
here.
bra, but the bra there.
So you have to path order. So if you have a time here and a time here, then the C minus time is always after the C plus time.
So when I compute sigma now, how do I really do that?
You calculate, for example, the 2pi action, right? I mean, if you have can, for example, calculate this guy. So you have a scalar and a fermion, right? And then you take just a functional derivative with respect to your field. So you can
To
take
your
this-
propagator.
Yeah. So this guy is a function of all your two-point functions, right? So this one contains 2 S's for the fermions and 1G for the boson. That's a boson, fermion, right?
Mm-hmm.
And then you say, okay, sigma In this case, it's a permanent one, so it's basically, roughly speaking, if you call this guy W, it's the W with respect to S, and then what you get is basically closed form. But it's a self-consistent equation.
So how do I know now if I'm computing which of these plus-minus combinations I'm computing?
Well, if you do it in
Matrix formulation, you're completely everything.
So when you compute,
you see, the effective action also has a matrix structure.
So you really use this matrix structure.
Sure. And then you sum of all indices that are summed over, right? When you take derivatives, some of those indices are broken, but there is still, you see, in this equation above, there is still a matrix multiplication to sigma and x.
Okay, so when this is always plus, yeah, or always minus, so it's not that you have mixed vertices.
Yeah. So usually, I mean, let's say you would like to calculate the plus minus, right?
Yes.
Then you put a plus here, you put a minus here, and when you look at equation theory, you use here the G plus minus to connect plus with minus, and you use the S plus minus here to connect the plus with minus. So you really preserve this matrix structure, and you can do it for the plus plus and for the minus equally, and finally you get again a matrix structure.
And then I have to do the derivative with respect to, sorry, when I'm, suppose I would like now to get sigma plus minus, I need to do the derivative with respect to S plus minus.
Yeah, exactly.
Oh, S plus. Sounds quite simple then.
It is.
Yeah, please do it.
No, it's very simple to derive those equations.
Yeah, no,
What's difficult is to solve them.
Well, first one has to have a well-defined starting point, so that one really can solve something.
Okay,
I mean, because my problem is these things always, there's this kind of abstract level as you've written it down there, and then it's really not to me never clear which sort of computations you would actually do. This is helpful.
But I mean, later on, in later stage, I will put all the interactions off. Just sigma will be 0, and still you get really non-trivial solutions.
Of course, there is this truncation that has been done implicitly. This is, you actually have a hierarchy of equations coupling all endpoint functions together. The sigma is a result of a certain truncation. Then you have a scheme to compute.
Yeah. Mm-hmm. In this case, it's 2pi. Yeah,
but in principle, this computation you've done is really just formally it's correct. It's just that you don't know what sigma is.
Well, and those two-point functions are of course not the usual ones. I mean,
no, I know. I cannot really do it because it's just a formal thing. I cannot do an additional step from there because I don't know what S and G are.
Yeah, exactly. It's a self-consistent equation.
Yes, but you still can draw these kind of diagrams, which you always like to do.
No. Well, but at level of diagrams, you can compute sigma, no problem.
Yeah, but then comes what Kimmo was saying. Now you need.
No, but the first equation is exact, isn't it?
Yes, exactly.
Exactly.
Well, it's also
I hate when people mention the word exact.
No, but it's exact.
I mean, exact in the sense that you cannot compute it. But let's talk about what you can compute.
Exactly, it's a question of how to define sigma.
Formation of the entire field theory.
Exactly, so it's.
Well, it is exactly the same. Yeah. It is exactly the same sense as saying that the effective action is just Legendre transform of the tree Laplace. And then you can say, oh, I have an exact equation for the effective action.
Yeah, I mean, this is
that's precisely the same statement as saying I can compute sigma, right?
Yeah, I mean, this equation also contains QCD at 0 temperature, right? So if you think you can easily solve it, then
well, you see, in that sense, it's exact. Not just at 0 temperature; it contains also QCD in very non-equilibrium situations like Rick.
Exactly. So the next step I wanted to talk about was this dependence on the average coordinate and this star product, which is necessary to make contact to the phase space in classical physics. So, and from now on, I will completely neglect interactions, in which case the equations become easier because this 2x2 structure decouples. So basically, you get two independent equations for two elements of this 2x2 structure, and the other ones are related to those two, which of course simplifies the problem a lot.
Sorry, how did you get these two now?
if you look at those equations and you just put sigma to 0, right, then you see that you get, I mean, two of them
just get one, I suppose.
are related because you know, okay, this guy plus the theta function should be the time order. So certain combinations of those two guys will give you the time order and the intertime order. Right? So basically they are just two independent functions here. Right? And
maybe it would be useful if you write the relation of sigma t instead of sigma in terms of sigma less and sigma greater. Can you write it down on the blackboard, then maybe this will become clear then.
Okay, I mean this guy is time ordered. This
yeah,
one
but
is
just write it down. Yeah. So for people who don't.
And this is then also true for all these other, like also in S and all these matrices. Basically, there are only two independent entries.
Yeah, you have. Yes.
So it's true for the propagators and for the self energies.
Well, I would just write it for the propagators.
I mean,
but doesn't matter. It's just the same structure, isn't it? Or is the structure different?
GT, for example. Yeah.
I mean, this is the time ordered of phi of this is T1 and T2. It was just the time order of T1 and T2, right? So it's basically theta of T2 minus T1 times phi of T1 and T2, which by the way is G less plus
the other way around. Phi T2, T1, late to the left.
Late to the left. And 1 minus T2. Time order is T1 minus T2 is the largest. In the intertime order it is vice versa, and so you.
And that's basically now you see the interdependencies.
So if you know G less and G greater, you can reproduce, of course, GT and G intertime.
There's basically only two orderings of phi, and the rest you can build up with two. And the same then happens also, the same structure you also have for the sigmas.
Yeah,
it's more complicated.
Well, in equilibrium it's you inherit it, but for wave in equilibrium you don't. Okay, so now I switch off interaction to make it a little bit easier and to decouple those matrix elements. And the quantity I'm finally interested in is actually this S less. And why so? Because I know in equilibrium this S less basically encodes my particle densities. So in equilibrium, I know that my S less is proportional to the on-shell condition. So that's just a dispersion relation of my particle and to the particle distribution function. So basically, my S less, if I integrate over the energies, I can read off this number, this function, which already appeared basically in the Boltzmann equations. Right. So somehow there's a hope that the Standard of Prime equation.
You're not talking about the bosons, right?
These are.
Yes.
No, this has to be. I mean, if I came out here, it should. Yeah, this one is boson.
Okay. Usually denoted by G, but it's fine.
Yeah. Wrong notation.
Okay.
Okay. So somehow there's a hope that the Gaussian of Prime equation gives you the dynamics of this quantity, like the Boltzmann equation.
But that this is n, or in the more general case, it's just. Yeah, it's just a definition of n, if you like.
Yeah,
which
it's
in
not a physical quantity.
And, yes,
it's like, I mean, like in usual Wigner space in quantum mechanics. I mean, you also can construct a phase space, but it's eventually negative. It can be negative, or all kind of things can happen when you have a real quantum system. But in the classical limit, you would expect that it goes to the classical quantity.
Mm-hmm.
Yeah, basically here S or G contains off-shell information as well, so you integrate over all possible shells, and this gives you some kind of classical constant.
And you later on use this as a definition of n.
Yeah, exactly. So far away from the
one of the definitions that you can use.
Yeah. So far away from the wall where you often effects, you would expect that this gives you the classical result.
This coincides with the zero component of the current.
If you integrate over all
scalar current.
This is only the particle number density, not the antiparticle density. So you have to integrate over all k if you want to get the current.
Yeah, but
so this is basically would be J0 if you want to integrate also over the negative k0.
Yes.
So you can,
yes.
and the relation to the currents is actually exact. So you can define the current by symmetry, and then this holds even if it's off shell to all
Yeah, so
generality.
this is
okay.
these are the positive frequency part of the netted current. And then
okay, that's a good statement. Yeah. Satisfying. That's why as good as you can, as close as you can get to a
yes. And
So
now,
definition of particle number in a more general context.
If you subtract from this or add to this negative part of the netted current, then that quantity should be conserved.
Okay, so the next question is how to get the Boltzmann equation or some kind of transfer equation out of the Cardan-Klein equation. And the simplest case is, of course, if you have a constant mass term. In this case, you can just look how those equations look like, the real and the imaginary part, and what you find are those equations. So what does those equations, what they tell you is, first one, this one is the on-shell condition, right? So this one tells you that your S less has to be proportional to this on-shell condition here, the dispersion relation. And this one basically is of Boltzmann type. So if you write it for low energies, where Kmu is basically the mass of the particle and the mass times the velocity, then you see that you exactly recover this flow term of the Boltzmann equation. Right? I mean, there's no force yet and there are no collisions because I neglected interactions. But nevertheless, it's nice to see that in this limit you can get back the Boltzmann equation. Okay,
It's
so
also called Lie equation. Lie equation.
yes, but it doesn't have a right hand side.
But yeah.
But here we have drawn away the second derivative.
yeah,
In
because the mass is not.
Yeah, but it's not on the mass, but the correlator.
And the
Even
Lie
the
equation
constant mass, the correlator can be
prove-
varied.
yeah, but this will
has a
turn out
conservation
relevant
flow.
in the mixing case.
On
But I
space
think here you can basically
Mechanics, course one.
neglect it up to the stage. Yeah, but it's true. You somehow you assume that already that the gradient expansion holds in this case. Okay, so now you want to do one step better, and you would like to include some real effect, like for example changing mass term. So if you have this Higgs background, and the Higgs surface is changing, your mass would be changing, and now you would like to incorporate this effect in your Cardan-Klein equation. So what you write for your inverse propagator is just this Z dependence on the mass, so you do it in the wall frame, where just everything depends on that. And then you expand this exponential operator, because otherwise, of course, there's no hope of solving anything. And the argument for doing that is basically that usually the Z dependence is rather weak. So you know that the thickness of the wall of your background is larger than your typical momentum scale, which is given by the temperature. So basically, if you compare those two scales, you see that this guy, which is basically the diamond operator, gives you a separation of 1/20 in each order. Right? So you do this expansion of this exponential and you neglect higher orders, and then you get the following two equations. Again, you get the same on-shell condition, so you know that S less has to be proportional to this delta function of the dispersion relation. But now you see that in the Boltzmann equation you get one term which you might interpret as a force term. Right? So if you go to the non-relativistic limit, this was basically just m times the flow of the Boltzmann equation. So this one is something like m times some force. Right? So somehow he managed to get a force from first principles. I mean, he didn't use any physical input. You just started with a kind of Bain equations, did certain approximations, and that's your result.
That's quite nice.
And now comes the reason why I talked about this particle reflection picture, because it turns out that if you have this high wall velocity, you are at the same time in the thin wall and in the thick wall regime, because they have different meaning in those two contexts. So that means in the regime of high wall velocities, you can just solve this equation in a certain approximation. You can just integrate it. And what you find is that your distribution functions does not just depend on u mu times p mu, which is, I mean, the usual thing. So I mean, usually we have n is equal to 1 divided by e to u mu p mu divided by t plus minus 1, right? But now, behind the wall, you get a dependence which is of this kind. And the interpretation of this term is, of course, just that the particle changed its z momentum from pz to this combination, which is roughly in first order of your expansion parameter equal to this guy. Right? So you see that in this limit, the reflection picture agrees also with the Cardan-Klein picture, which is a nice result. So somehow this quasi-particle picture of reflection works in this limit. Okay, so next step is of course CP validation. And
Sorry, and again, this expansion would break down if you go to low k.
yeah,
Then again,
but there are not many low Ks in this case. So
Yeah. So what Thomas is now basically saying is like if you look at the kinetic equation and the constraint equation, basically the constraint equation can be also viewed as the integral of the kinetic equation, and the integral of the kinetic equation is consistent with those two solutions that he presented with, you know, just by ballistic particle motion.
So you will. Oh yeah, basically now you go one step higher in the expansion.
yeah.
Okay.
Okay, so next step is you want to do even better and include some CP validation. And the easiest way of doing that is having a fermion Dirac particle with a mass which has a complex phase which is changing along the wall. Right? So that's the first CP validation you can introduce in a simple system. And again, you can try to solve, I mean in this case it's a little bit more complicated because you have a Dirac structure and you have to decouple this Dirac structure to get some particle number. But what you finally get is a kinetic equation of this form. So you have this old force we just found, which is of course CP conserving. But now you get a second force which is proportional to the spin. So I mean to decouple you have to project on the spin of the particle. And you see you get one force which is proportional to the change of this phase in your mass, which is CP violating.
Thomas, I hate to say this again, but you know, in this community, maybe I should say, I actually was also involved with that one. I know you all read the Opus Magni, which is but this result actually was without into earlier papers where I was hanging around with these guys, right?
That's correct.
That was in the cover of Binding?
Yeah.
Yeah,
Sure.
Oh, okay.
Two papers where we
I didn't know
tried
that.
first in one dimension and then in three dimension, both
Yeah.
of these results.
Yeah, but thanks for pointing that out because
I was just thinking if you show this somewhere else. You know. If you do in French, it's okay.
Yeah. No, included. No.
That's the thing. There was a quotation.
Yeah. That's
And then this is basically which agrees with this WKB approach, which was done earlier by Kim and company. So somehow it's interesting to see that you really get a CP violating force out of this kind of binding approach from first principles. Because in this WKB approach, somehow you also have to fill this gap by hand by interpreting the force as a derivative of the expression relation.
So it's always nice to study a scalar field.
Yeah, in the scalar case,
what
nothing
would you do? What would happen there in the second order?
Nothing.
I just like a real scalar field.
I'm not
You
even
say
sure if
you say there's no term which comes to the second.
No.
No.
It's just zero.
So,
So the
You have
third
to go
order it's only odd orders which
you
you
see,
get.
this one is proportional to S, spin. There is no spin in the scalar case, so there is no such effect.
So for the scalars you get only the odd ones.
Higher one.
So you get like this, I don't know,
Yeah.
this
You
one
know,
derivative which we just
This
saw.
is really fantastic conspiracy in the nature that for fermions, to this order, the lowest order, this is not the lowest, but it's first order effect. The important effect comes in the first order, which is really the highest order you can compute.
Yes.
You see
This
the,
is the dominant
Yes.
effect, actually. If you compute the second correction, it's
maybe
wrong.
maybe I can explain the following by in the fermions. For the fermions, you have two independent currents: axial vector current and vector current. While for the scalars, you only have one current. So there is no source also for fermions at the level of vector current, just like there is no source for scalars at the level of vector current. However, this source will source axial vector current for fermions, and that's unique for fermions, and that's why there is this source.
Precisely.
So but can you write? Is the equation known to second order for the scalars? I'm not saying that you can solve it.
Can write it down, but
Zero.
Yeah,
Just isn't
then
the,
it's
just
There's
zero.
no extra terms. There's no
Exactly.
extra term.
There
The
is-
second order looks like the first order. equation.
Exactly.
Yeah, there is, precisely. There is similar term to this first order, DZM, we just... is the
Yes,
normal
yes,
equation.
yes.
But-
There's no CP violation.
Exactly. However, when you look at flavor mixing in the scalar case, then there is a source,
You
and
also
that
can get the source of this.
I guess Thomas will mention this. Yeah.
So that you expect at third order there would be one, but then you have no hope of solving these equations.
No, if you have several flavors, you get also
No, if I have one,
in this order.
I'm not even talking about CP violation. I just would like to understand the structure of the equations.
Yeah, there's nothing.
So there's nothing at the second order. There would be a term at the third order, which okay.
Yes.
Sine operator. You have all the power with the sine function, basically. Sine, you break the exponential of that time into cosine and sine, and that contains the derivatives of sine.
Ah, okay. So you say basically.
Third order, fifth order.
Yeah, it's basically, I mean, if you look at this Moyard star product, I mean, you have an I, and then one equation is the real part, and this one is the imaginary part.
This is not used.
So it's basically, so second derivative terms will appear in the constraint equation, and third once again in the kinetic.
Exactly, and the problem with scalar, even though there is an effect on third order, if you now try to solve consistently the constraint and the kinetic equation, you'll find that there is no local source in the sense of here. You know, here at the level of energy, I can still talk about local shift in energy and the corresponding force, which is also local. But for scalars, even if you did go to the third order, you will still find that there is no such simple local description. So we are really lucky here.
Yeah, that's why it's wonderful constraints.
Yeah.
Even, you're completely small effects, so of course there would be a high order corrections as well, but you don't need. This is
Well, if the wall is thick.
Well, maybe that should be
but
left for
then it
the...
doesn't, then it's so small that it doesn't work anyways.
Is that clear?
Well, I would say it's premature to say that.
Yeah. Okay. Let's continue.
Yeah. Okay, so if you now want to take care of the other effect, the mixing, it's much harder to decouple the equations. So what I wrote down here is basically a fermionic equation where I already projected on spin, but basically that's the guy you have to solve. And
Maybe you should explain what S's are here.
S's are again the Green's functions. So those are 2-point functions, but they also have a 2x2 flavor structure in this case.
So why don't you just define it?
Okay, it just has an additional flavor index compared to the water. And the masses also have a flavor in the metric structure and flavor space, but those are basically the equations you have to solve.
S is the fermionic propagator, which is the element of Clifford algebra, so it's a 4x4 in matrix structure.
Yeah, so
and then
there are different S's because you have different So this one is the S0 and you have a flavor index.
So these are components in the block expansion. Block representation.
So you can make the...
Yeah. And you have a SCM spin protector.
Pauli.
It's called block representation.
Block, yeah.
Yeah.
Well, basically what you have is you have a 4x4 structure of these equations, and in this case, when you have a Z-dependent background, then this 4x4 matrix structure actually breaks down in the block diagonal structure, 2x2 blocks.
Yeah, because spin is
each of them is denoted by spin, and so in each of those 2x2 blocks, which has a definite spin, there are 4 functions, and these 4 functions correspond to scalar, pseudoscalar, vector, pseudovector densities, and they're denoted by S0 to S3.
Well, it's getting complicated. That's what I wanted to say with this picture.
No, why?
But one thing you can do, and it's most probably the most reasonable thing to do, is you just expand around your equilibrium, and then finally you get something which is of this form. You get again this Boltzmann type of kinetic term. Now you get a new term which basically accounts for flavor oscillations like neutrino oscillations. Then you get all kind of sources and forces which are involve just the equilibrium function. And on the right hand side you have to keep in mind that in principle there still can be some collisions. Right. So but the interesting part here compared to the one flavor case is basically that you have those oscillations. Because this oscillation is basically one effect which has completely neglected in this old work by Karina Wagner, and who first promoted those mixing effects. And basically what it tells you is that if your masses are almost degenerate, then the oscillation will be slow. But if the masses are not degenerate, then you have a fast oscillation. And this fast oscillation will basically wash away all kind of integrated effects you might have in the plasma. So,
sorry, how do I see that this effect becomes important only in the degenerate case?
okay, it's not so easy to see, but if you look at CP relation in your equations, at your sources, you see that CP relation has to be generated on the off diagonals. And the off diagonals are the elements which oscillate. So if they oscillate fast and you integrate over Z finally, this effect will go away. And that's
Because fast
basically...
oscillations are damped, and the damping is very efficient in fast oscillations. That's quantum decoherence.
Yeah.
So what is the other scale?
So there's no scale, it's basically H-bound separation. So if you
No,
would
no,
make
no,
the-
I mean, when you say at some point the oscillations become frequent relative to what scale? Like transport
oscillation
scales?
scale is given the mass difference between the two particles.
And you have to compare it to the damping, which is
To
basically
them,
the
to
linear
transport,
part.
to transport.
Yeah.
Right. So, but it's also in some sense a classical limit. I mean, if you send h bar to 0, you have a 1 over h bar in your oscillation frequency, and oscillation becomes fast, and it will damp away all quantum effects which are off diagonal in this picture. Okay, so if you now look at the sources, what you find is, first of all, you can, of course, recover again this WKB force, which we talked about before at second order in the gradient expansion, so you have two derivatives. But you also find sources which are first order in derivatives, and those correspond exactly to those sources formed by Carrena, Moreno, Quiros, and Wagner in the original paper of the analysis. So somehow the canon of Bain equation is really powerful enough to unite those two effects, and at the same time solve some question of ambiguities and how to connect it to transport. So it's really a first principle approach. You just start with a kind of Bain equation, and then, I mean, you have to use a lot of approximations, but there's no hand waving, no classical input in some sense.
Well, I mean, the only approximation you use is that your gradients are small, and so you do consistent expansion in gradients, and you truncate at some order, right?
But I mean, those approximations which are well under control. I mean,
Sure, that's what I'm saying. I mean, you sounded like you're putting something under the rug, but it's actually not the case.
But these sources appear in a very different way in the actual diffusion equations.
Yeah, exactly. It's
So that although this source S1 is by numerically larger, but
Well, Kimo, you see, this source, there is a crucial difference. This source couples to S, and this S is non-equilibrium mass. So you can actually separate the equilibrium part and then calculate, and also you already have now the source automatically in the diffusion equation already here. Well, they could never get this.
yes.
So this is the first important advantage. The second important advantage of this is by solving the actual equation where you have a source like this, you can actually resum over all mass insertion. And the third important is that this is manifestly base independent. So, I mean, there's three important advantages of this formulation.
But you always go to a certain base, and I think you also wrote that if you go to a different base, it becomes really ugly.
no. I mean, it becomes. I mean, it's explicit. I mean, you really have this 2x2 structure. If you change your base, you still get the same result. Eventually it's easier to calculate your result numerically in one base
Yes,
than the
that's
other.
what I mean. Yeah.
Because, I mean, if you go to the mass eigenbase, you have oscillations just on the off diagonal. Well, if you go to the interaction basis, I mean, oscillations will whatever.
Yeah, but you also make an ansatz that you have your zeroth order solution is equilibrium distribution in the mass eigenbases. So in that sense, it makes a difference.
But that's your equilibrium, which is picked by.
Yeah, okay, but it still makes a difference. It's not completely basis independence when you solve them.
Well, you pick a basis in which you solve, but the actual formula is in the basis.
Yeah.
Manifestly, yeah.
I agree.
Yeah, exactly.
Intermediate steps.
Yeah, I mean, at some point it's of course lost if you do linear analysis. Okay, so which steps are missing? The first one, what you have to do is you have to communicate this P relation to your quarks in the standard model, and then you have to act on it with this follow-on.
Sorry, can you? So you expand in gradients.
Mm-hmm.
Is it does it come somehow clear when it really will fail?
That what?
So if you compare with the wall thickness, so L thickness times T, I guess, is
Right.
a crucial parameter. So when do you expect it to fail?
Well, that depends on your model. I mean, in the MSM, for example, you know that your walls are rather thick, right?
no,
you know
I mean,
that L is like 20 over T.
so yeah, that will work fine. Do you think for 5 it also works fine?
Well, I mean, at some point, of course, I mean, if it's 1, I wouldn't trust it anymore, but at 2 or 3, you wouldn't expect that there's some effect which annihilates. I mean, you would expect that the order of magnitude is the
So I
same.
think 5 could still be kind of...
Right, and you would say, okay, eventually factor 2 is wrong, but you wouldn't expect that it's 0. And you wouldn't expect that it's factor 10 bigger. So there's one step missing, and that's a communication to the standard model particles in this follow-on. And there are different works on that. And the most recent one is basically by Björn and collaborators, where they include all kinds of different particles. And the sources which we just calculated in the Giardino sector. And by doing that, you can predict the baryon number which finally results from this mechanism. Okay, so what about the advantages and disadvantages of this Kardanow-Bine approach? First of all, I mean, the technical advantages, of course, there are no ambiguities. You really just use this Kardanow-Bine equation. There are no divergencies, which is a big advantage compared to this perturbative approach by Carrera et al. And Kiros and Wagner. It includes both effects which have been studied before, the WKB and the mixing effect. So you have really one uniting picture. And in addition, you found those flavor oscillations which have been detected before.
You mean there are no divergences generated by thermal distributions?
No, it's divergencies because you use perturbative methods, and then...
Yeah, but there's still vacuum divergences, of course.
No, I wouldn't think so. Because, I mean...
Well, there are.
In the beginning, what people do typically is they use those thermal propagators, right? But they introduce, I mean, the result will be infinite. And what they do is they introduce a thermal width in your propagator.
I thought
I
you
know,
were
but
doing something
these
similar.
are thermal divergences they obtain because of incorrect application of the formalism.
In some
But
sense,
I'm talking about simply there are vacuum divergences just in the standard field theory.
yeah,
They're still there, and
those
the
divergencies are not the ones they found in the formula.
of course, yeah, there's, yeah, sure.
But I thought you also have to introduce a width. So if you remember your
No.
MSSM paper, there is a parameter there which you vary and you don't really know what it is.
It's a different one because I mean what you do in our approach is what you do. You know what happens close to the wall, right? You go out of equilibrium, and then you mimic a collision term usually by introducing minus gamma g, right? Which so if you have a sum out of equilibrium here, which drives you back to equilibrium far away from the limit, right? Because otherwise you would just go to a constant value, which is kind of unphysical. I mean by doing that we mimic collisions. But in their approach, what happens if you send this gamma to 0 is that the source diverges. So it's a completely different.
Don't need it completely master general.
Yeah, I mean, you can trace this problem back to the original paper by Ryota. And in his paper, you actually see if you send, he actually writes down the solution of thermal propagators, but now including some finite width. And then calculate some source, and in his calculation, if you send the width of the Green's function to 0, you will get the divergent answer. And that simply means that there is something wrong in the calculation procedure. It does not mean that there is something wrong with Friedrich formalism.
But in the end, what you probably could compute in the quantum filter is like, in the end, you would maybe like to get the baryon current as well at one side.
No,
And
but
typically,
I'm
I think when you compute these things, if it's a conserved quantum, I guess quantum field theory protects you from getting additional divergences, which is probably not true for the baryonic one. In a sense, it's not a conserved
Yeah, but
one.
you know what we are talking about divergences that have nothing to do with quantum divergences of field theory. These are divergences that occur in certain calculations when you inappropriately apply Schwinger-Keldysh formalism to this type of problems.
Underline the word inappropriate.
Yes.
It was frustrating because it was so clear that it's wrong. These people were just churning on papers based on this.
Yes. And they put this finite width and claiming, oh, this finite width is there because it is true it's there. But you should also get a finite answer if you set the width to 0. I mean.
Well, I'm not so sure about this one because it's a question of consistency. So, I mean, per se, I would not expect that this procedure leads to a divergent result. So I think if you do everything correct, you would expect all the divergences cancel.
Yes, but they didn't do it correctly.
Right.
Yeah.
But I mean, to explain where the divergence comes from, I mean, what they basically do is they calculate they have an insertion which is a change in the mass, right? And they calculate a diagram of this kind. So you have the same propagator here and here because you have no momentum here, right? So what you get is kind of a pinch singularity. so that's basically the reason why you get a divergence in this picture. But nevertheless, I mean, in some sense, I mean, if you really would solve consistently all the Kazanov-Bime equation, it would predict gamma, right? So in some sense,
No?
yeah, of course. If you take into account interactions.
No, gamma is no. I'm sorry. Well,
We have a collision term.
well, gamma in the sense
No, even in equilibrium, you would get a finite gamma.
that is correct. Yeah.
Right, and so in some senses, gamma is of course physical, but
No, but the source for finite source you don't need any gamma. I mean, you can set gamma to 0.
in our picture, yes, but it's I mean, it's a different way of solving the kind of Bime equation. Because
Well, is it somehow, I actually forgot how it goes, but this is somehow, the singularity comes from, you assume that your mode is massless, so you have infinite divergence between these lines.
No, it's...
So, but if you resum the mass, then you don't have the infinity.
That's basically,
Actually,
yeah.
the source is also proportional to mass, so if you have resummed it and then put the mass away, your source goes
Exactly.
away as well. I mean, so there's no singularity there. But here you can put the mass, you can keep mass finite and, you know,
That's
Yeah, I mean-
precisely, yeah. That's
I mean,
precisely.
what you of course would expect also is that,
seem to have infinite source.
that in the limit of small coupling that your the effect doesn't diverge.
Yeah.
I mean, that's of
Yeah.
course what you require, but I wouldn't be sure that you always get a divergence in this kind of
Conversion dance.
Yeah.
You do. Unless the gradient expansion breaks down.
Yeah, I mean, the problem is that on top of this approximation, you do a lot of approximations which eventually not.
But I agree with Thomas that this result does not need any gamma to give a finite correct result everywhere. Mass takes care of the regularization
Yeah,
and puts
yeah.
the source away when the
Yeah.
mass goes away. So there's no problem. You don't need
Precisely.
any gamma.
Precisely.
Well, I think the question of how, for example, let's say you get this shift in the dispersion relation, right? So you get a delta p squared minus m squared plus delta m squared, right?
Yeah.
So what happens if you do now an expansion in this delta m squared? I mean, what you get is you get a delta m squared, you get something which is of delta prime, right? Which is usually even. So this guy will give you a divergence. So I mean, it's just a different way of saying why in this approach you get a divergence.
Yeah,
right?
but that's why you should solve the equations rather than doing mass
I mean,
insertion.
there's of course the advantage of the Kazanov-Bime equations, but nevertheless you could undo this and reconstruct this and you
Yes.
get the correct result.
Exactly, which is completely finite. That's
Yeah. Okay, so but there are two big points I would mention is, I mean, what we did in our, I mean, it's not a problem of the formalism, it's rather a problem how we are nowadays in the MSSM, and what we did in the MSSM didn't include any quantum transport in the quark sector, so somehow we didn't take into account quantum back reactions into the Giardino. So what we did is we calculated the p relation in the Giardino sector, and then we transported it somehow in the quark sector. But I mean, a complete treatment, of course, would make it necessary to calculate all the collision terms and all the flavor dependence between the Giardinos and the quarks, which wasn't done yet. Okay, so time is flying, so I guess I just skip this part about models. I just highlight what's interesting here. And the point is that in the MSSM, the dominant process comes from this mixing. I mean, and since MSSM is everybody's darling, there was this large discussion about mixing, how to include it. Even so, nowadays it's extremely constrained scenario, and as Michel said, well, I wouldn't bet money on it anymore because to fulfill a lot of constraints to get a first order phase transition, to fulfill EDM constraints, and to get CP violation margin. And then you have to get Giardino's master generate, which is
some people bet money even if they know they're going to lose. You know how it is.
But there are models which are also well motivated, like the NMSSM, which is motivated by the new problem of the MSSM, and here you get a completely different effect for CP violation because you really have this semi-classical force in a Cyclin field which you added to the model. And here the story is really that you can forget about those mixing terms. Life is much easier. You can use this approach with WKB and you find that in this kind of model, electric biogenesis is kind of generic. So in a large part of the parameter space, you really get electric biogenesis.
So you don't need this Giorgino degeneracy.
Exactly. So you just have the classical force, and you know what happens because you always work with classical particle densities, and you know how to couple everything and how to get diffusion.
Yeah, then you can just couple this to the, I don't know, to this diffusion equation everybody uses.
Exactly.
And you still get large EDMs.
Well, yeah, it's borderline. Yeah. But it's easier because the walls are thinner, which makes CPU relation a little bit more pronounced.
So what makes this argument that M2UC small product?
No,
You can make it.
you just make it small because you don't need it for electric
So you don't need
biogenesis.
it as far as
Yeah, so that's the point.
EDMs come from, well, CP violation comes from different sectors.
It comes from the singlet
Yeah.
sector. So
Singlet sector,
yeah.
of course, yeah, yes.
Okay, so the conclusion is I think it's nice that you have this first principle approach because you really can understand what happens and you can fill some gaps which formerly have been filled by classical arguing and those problems that arise in this mixing approach especially. And it's also nice because you can unite those two effects which have been discussed separately before. And there might be other applications like, for example, flavor heterogeneous where you might eventually hear something soon.
Yeah, but I mean, yeah, it's interesting that you emphasize this because actually there was Wagner and Karena and somebody else, I think, at some point wrote a paper claiming they have a derivation to show that these two effects are actually equal.
Yeah, well.
I mean, and obviously that paper is incorrect. So at the level, in year 2000, there was a complete confusion about what was the correct source and how these two types of sources are related. And so, well, I hope that, we have learned this now from Thomas's presentation.
Yeah, let's thank Thomas.